Recalling the continuing theme that we will never know the truth, what can we really conclude when we conduct a hypothesis test? Imagine for a moment that we actually do know the truth. This table gives us all the possible outcomes of a decision we might make concerning a particular hypothesis. 2 are correct decisions, and 2 are errors. If the null hypothesis is actually true, and our test says we cannot reject it, then we have made the correct decision. The status quo stands. If, on the other hand, the null hypothesis is false, and we conclude we cannot accept the null hypothesis, then again, we are correct. We have rejected a false null. The other 2 possible decisions, however, are a different matter. In both cases, we have made an error. Each type of error is given a name. If we reject a good null, think put an innocent man in prison, then we call it a type 1 error. If, however, we cannot reject a false null, that is, we accept a false null, then we have made a type 2 error. Here we have let a criminal go free. The null was innocent, and the evidence was not sufficient to reject the null, when in fact he was a criminal. Each error has a probability of occurrence. The probability of a type 1 error is called alpha, and yes, this is the same alpha we met doing confidence intervals. Before, alpha determined the level of confidence, and it will do so here also. The probability of making a type 2 error is called beta. We can control only one of these 2 probabilities, and we choose to control alpha, the probability of putting an innocent man in jail. That is, the probability of rejecting a good null. Remembering that the null represents the status quo, this amounts to controlling the probability of overturning the current way of understanding the world. The system is designed to control how fast we decide our current way of thinking is wrong. The statistical test is biased in favor of retaining the null hypothesis, the current worldview. That is to say, if we are to make an error, it is in favor of the null hypothesis. In the example of the criminal justice system, we put the burden of proof on the prosecutor. Thus, we'll set the alpha level, the probability of rejecting a good null, innocent man goes to jail, at a very small level. This, of course, means that we have a very high confidence that we did not make a type 1 error, send an innocent man to prison. The easiest way to see this relationship between the alpha error and the level of confidence is with the following figure. In the center of this graph is the normally distributed probability distribution marked H0. This is the sampling distribution of X bars, and by the central limit theorem, it is normally distributed. The distribution in the center is marked H0 and represents the distribution of the null hypothesis. H0 is mu equals 100. This is the value that is being tested. The formal statements of the null and alternative hypotheses are listed below the graph. The distribution on either side of the H0 distribution represents distributions that would be true if H0 is false, under the alternative hypothesis listed as HA. We do not know which is true, and will never know. There are, in fact, an infinite number of distributions from which the data could have been drawn if HA is true, but only 2 of them are on the graph representing all the others. To test a hypothesis, we take a sample from the population and determine if it could have come from the hypothesized distribution with an acceptable level of confidence. This level of confidence is the alpha error and is marked on the graph as a shaded area in each tail of the H0 distribution. Each area is actually alpha over 2 because the distribution is symmetrical, and the alternative hypothesis allows for the probability of the value to be either more than or less than the hypothesized value, called a two-tailed test. If the sample mean, marked X bar 1, is in the tail of the distribution of H0, we conclude that the probability it could have come from H0 is less than alpha. We consequently state the null hypothesis cannot be accepted with 1 minus alpha level of confidence. The truth may be that this X bar did come from the H0 distribution, but the sample was from way out in the tail. If this is so, then we have falsely rejected a true null hypothesis, and we've made a type 1 error. What statistics has done is provide an estimate with a known probability of being wrong, called alpha, and this probability of being wrong is under our control. We can also see in the graph that the sample mean could actually be from one of the HA distributions within the boundary set by the alpha level. Such a case is marked as x bar 2. There is a probability that x bar 2 actually came from HA, but shows up in the range of H naught between the two tails. This probability is the beta error, the probability of accepting a false null. Our problem is that we can only set the alpha error because there are an infinite number of alternative distributions from which the mean could have come that are not equal to H naught. As a result, the statistician places the burden of proof on the alternative hypothesis. That is, we will not reject a null hypothesis unless there is greater than 90 or 95 or 99% probability that the null is false. This system of how we decide what we believe and how we move from one worldview to another is deeply embedded in the scientific method, which is the guiding principle on such matters. There is a lot at stake here. We should be as aware of these issues as we are of the math formulas we will use to do the specific tests of hypothesis. In a real sense, these formulas are the mechanics, while these issues are the philosophy, which has a powerful impact on policy.